Good afternoon, everyone. This is College Algebra, College of the Sequoias, Spring 2020. And we're working from home for the COVID-19 pandemic. Today, we're going to cover logarithmic functions. We started off this chapter, chapter 4. It's on exponential and logarithms. 4.1 was on inverse functions, and 4.2 was on exponentials. 4.3 is on the logarithmic functions. And they come in the form y equals log, and then they have a b down below. It's called base b x. Maybe I'll make it a capital B because my lowercase b's look a lot like sixes. So b is the base for the log. And x is our argument. And this has the equivalent form of x equals b to the exponent y. So that's how these kind of relate. Now, in y equals log base b of x, we want x to be greater than or 0. And we want our base to be positive as well. And we also want it to not equal 1. And what does this mean? The expression log base b of x represents the exponent that our base b needs to be raised to in order to obtain x. This makes a great flashcard. This set right, this data right here, great flashcard. Put one on one side, one on the other. It's important you know these are interchangeable. Okay. So why don't we practice doing some conversions? I'll pause for a second, let you finish writing this. All right. Let's practice doing some conversions. So on the left, we're going to have our y equals log base b of x. And on the right, we're going to have x equals b to the y. So let's start off with 4 equals log base 3 of 81. How can I switch that over to x equals b to the y? What you might find handy is comparing these. Thank you, honey. Say hi to my wife, everyone.
Hi.
There she is. All right, back to work. So let's compare what we have. Our y lines up with the 4. The b lines up with the 3. And the x lines up with the 81. So let's put them where they belong over here. 81 goes for x, b goes with 3, and y goes with 4. Is that true? 3 raised to the 4th power is 81. I told you they were the same. Now I want you guys to try. I'm going to give you several to work with. Let's take a look at log base 1/2 of 8 equals -3. We'll look at log base 5 of 1 over 125 equals -3. We'll look at log base 10 of 1,000 equals 3. Log base 12 of 12 equals 1. Okay, pause the video and practice converting. Okay, I'll assume you did. What do we have here? We have y equals -3. Our base is 1/2, and x equals 8. This says x equals b 1/2. X is 8 to the -3. This one, our x is what's the argument. Oh, did she lock you in here, baby? Go on.
I didn't know he came and followed me.
Sorry about that. The dog got trapped in the room and he was starting to whimper. He's a little whiner. So x is our argument. It's what's inside. It's the 1/125. Y is the other side, which is our exponent. And our base is down there. It's the 5. Here, 10,000 equals x, or 1,000 equals x. Our base is 10, and the side by itself is our exponent, 3. And here, this is our base. This is our exponent, and that equals 12, our x. Okay, now this last one, actually, this holds true for any b. Log base b of b equals 1. Of course, b needs to be greater than 0. That was part of it. And what does this tell us? This is my x value. This is my y value. B comma 1 is on every log graph. Every logarithmic graph. Now, let's look at our files for a second. I know I posted something for you recently. This a must-watch video. He shows you logarithmic graphing. He shows exponential graphing as well, but what he shows at the end is a logarithmic graph, where that each axis has different scaling as it goes. It's the exponents. They do this in the Richter scale for earthquakes, and they do this for a lot of things. Okay. So that's a good one to have. That's a good thing to know. Or what else appears on every graph? Log base b of 1 equals 0. This is the same thing as saying 1 equals b to the 0. That's my X, that's my Y. 1, 0 is on every log graph. And finally, the other one that appears on every log graph, we know that b to the negative 1 equals 1 over b. So log base b of 1 over b equals negative 1. And we get 1 over b comma negative 1 also is on every graph. So we got b comma 1, 1 over b negative 1, and 1 0. This looks pretty familiar. Let's literally write it out. Every log graph has 1 over b comma negative 1, 1 0, and b comma 1. What if we change the order? Negative 1, 1 over b, 0, comma 1, and 1, comma b. Does this look familiar? What if I said b equaled a? And I had 1 over a, 0, 1, and 1a. These were our base points on the exponential graph. And these are our basic points on the log graph. And the x and y switched. And what do we know about when two functions and their x and y switch? We covered that in 4.1. They're inverse functions. Neat, huh? So let's plot some basic log graphs. We'll start off with b equals 2. So y equals log base 2 of x. That tells me I've got the point 1/2, negative 1, 1 0, and 2 comma 1. I said x has to be greater than 0. That makes x equals 0 in asymptote. And that's our y-axis. So that's why I'm making a dotted line right here. Our x-axis is fine. I've got the point 1 0. I've got the point 2 1. And 1/2, negative 1. It goes like that, going to the right. And it Tron cycles along the y-axis. And we can see that over here. That's our graph of y equals log base 2 of x. Never hits the or the y-axis. If we look at y equals 2 to the x, the exponential function, it looks like that. And what if we put our line of symmetry in there for inverses? Look at that. They look like mirrors of each other. All right. What happens if we what if we flip B over? If the base flips over, what happens? Guess what? The graph flips. Let's take a look at B equals 1/2. So 1 over B is 1 over 1/2, which is 2. So the point that goes with -1 is 2. 1, 0 is always there. And we said B1 is always there. Nope, that one's solid. We got 1/2, 1, 1, 0, 2, -1. Like so. So we can see it right there. It's flipped over. The orange is coming along here. The blue is going along there. And the orange goes up and follows the y-axis upwards. We can see it. It's following it upwards. Whereas when the B's normal, it's upside down, or it's like that. It's kind of neat. That's how we basically solve them. And we can look at that last one. We can compare it to the exponential. And we put our line of symmetry in, and you can see it's a reflection right across that y equals x line. Good stuff. All right, so let's take a look at solving logarithmic equations. So let's look at a few. We got log base x of 16 over 9 equals -2. The way we want to do this is rewrite them in the exponential form. So it might be helpful to point out what these are. This is B, that's my old x, and that's my y. And we want to end up with x equals b to the y. So how do these line up? That's my b, that's my x, and y is my exponent. Which means that's 1 over x squared, right? So I have 16 over 9 equals 1 over x squared. I can either flip them or we can cross multiply. Let's cross multiply. We're basically clearing the fractions. 16x squared equals 9. We divide by 16, and we get x squared equals 9 over 16, which is why I said we could flip it. This is flipping them. We take the square root of both sides, and we get x equals plus or minus the square root of 9, which is 3, over the square root of 16, which is 4. But we had the criteria, x has to be greater than 0, which means our only answer is the positive one. X equals 3/4. There we go. Now I can write more naturally. Sorry, the camera's wobbling. It's on a tall box right now. In fact, you might actually like the way it's set up. Let me show you how it's looking. It's like the little Pixar camera light. You know, when you see a Pixar movie, that's what we got. That's the document camera that I'm using. Okay, let me give you guys one to try. So we're going to do log base 16 of x equals 3/4. Identify your b, your x, your y. And if it's necessary, rewrite the general form real quick. Log base b of x equals y. That way it might make it handy and easy to see what lines up. B is 16. Our x is x. And our y is 3/4. This turns into x equals b to the y. And so we put those in. X equals 16 to the 3/4. So how does that work? Well, remember we played around with radicals a lot. This is saying we can say 16 to the 1/4 raised to the 3rd power. And that's the 4th root of 16 to the 3rd power, which is 2 to the 3rd power. So x equals 2 cubed, x equals 8. All right. Let's give you another one to play with. Log base 36 of the square root of 6 equals x. Identify your b, your x, your y. I've given you 3 different examples. The variable has changed position in all 3 problems. So I'm going to write it again below it. This is my x, b is 36, and x is the square root of 6. So I'll rewrite this in exponent form. I have the square root of 6 equals 36 to to the y, which is x. So here I've got the exponents in the variable. This is where we want to get a common base. Get the same base on both each side. This is 6 to the 1/2. 36 is 6 squared. So I have 6 to the 1/2 equals 6 to the 2x. Once we've done that, we can equivocate the exponents. 1/2 has to equal 2x. Divide by 2, or multiply by 1/2, and we get x equals 1/4. All right. Let's see, where am I? Okay, next problem. Or not next problem. Let's discuss the properties of logs. Properties of logarithms. And I'll show you how we derive them. We will derive the first property. I'll show you where we get them. And if you want to derive the rest, you can. The rest are derived very similarly. So what we're going to start off with, I'm going to start off with two things. I've got log base b of x equals m. And I'm going to say log base b of y equals n. Now, if I rewrite this, this is b to the m equals x. And this is b to the n equals y. And now what I'm going to do is I'm going to multiply these together. So I have b to the m times b to the n equals x times y. And the rules we have for exponents says I can make that m plus n equals xy. And I can switch this back to logarithmic form. Log base b of xy equals m plus n. But I already have what m are right up here and right here. Let's bring those down. We get log base b of xy equals log base b of x plus log base b of y. That's where we substitute in on the right-hand side. One way to this is one of the rules. It's one of the properties. And one way to think of it is multiplication on the inside of a log equals addition outside the log. So that's how we derive them. I'm going to give you the table now. And they all follow suit. We could do the same thing. We could divide. So I'll pause, let you, if you want to finish writing that. And let's write down our table of properties. We just got done showing the first one. Log base b of xy equals log base b of x plus log base b of y. That's our first one. The second one, if we have division on the inside, this turns into subtraction on the outside. And it's done exactly the same way. The setup's the same. Log base b of x to the r power is the same thing as r times the log base b of x. Oops. The way I remember this one, exponents can be pulled out front. Two of these we've already talked about. We've got log base b of 1 equals 0. And log base b of b equals 1. So if I say like this is A and this is B, if we combine these two, A and B together, log base B of B to the x power equals x. How does that combine? We have log base B of B to the x. We use A to rewrite this as x times log base B of B. And we use B. B says this is 1. So that's how that ends up working. And the other one we have, B to the log base B of x equals x. And both of these are related to the idea of inverse properties. Remember we said f of g of x equals x and g of f of x equals x? Same idea. So those are, let's see, we've got 1, 2, 3, 4, 5, 6, 7 properties. We will have at least one more. And I'm going to do it in this video, even though it's 4.4. 4.4 is really short. Let's apply these properties. Let's get some practice in applying these. Okay? You might want to have this readily available next to you. while you're working on these until you have them memorized. So A, we're going to do log base 7 of 8 times 6. I can rewrite that as log base 7 of 8 plus log base 7 of 6. Okay, next one. Log base 6 of 12 over 5. Why don't you guys take a second and rewrite that as 2 separate logs. Okay. Division led to subtraction on the outside. We got log base 6 of 12 minus log base 6 of 5. Let's see if you get number C, or letter C. Log base 3 of the third root, or root 3 of 9. What does that equal? Okay, hopefully you pause it and try to work on it. What we're going to do is we're going to rewrite that 9, or the cube root of 9, as 9 to the 1/3. And if that's what you needed, I'll pause again and let you work from there. Okay. The exponent on the inside can be pulled outside. But wait, isn't 9 3 squared? Which means I can pull a 2 out front also. And we have log base 3 of 3. But what does that equal? It equals 1. So this whole thing cleaned up to 2 times 1/3, which was 2/3. We didn't even need the logarithm in there when we were done. Now, technically, we don't need the logarithms in the other one. We could put them in a calculator and get a decimal version. Let's make a tricky one. So we're going to have log base b r s squared t over u cubed v to the 5th. And I want you to rewrite all of this as separate logs with no exponents. And no fractions. There's a couple ways of doing this. Let's talk about them both. The first approach A, I could treat this as log base b of r s squared t minus log base b of u cubed v to the 5th. That was our division turns into subtraction. Then I can separate these out. I've got log base b of r plus log base b of s squared plus log base b of t minus log base b of u cubed. And the minus applies to this whole thing. So this is going to be minus log base b of v to the 5th. And finally, I can pull the exponents down. I get log base b of r plus 2 log base b of s plus log base b of t minus 3 log base b of u minus 5 log base b of v. Another way you can look at it, and I'll just do the first step. That's the problem we started with. Rewrite the things on bottom as negative exponents. And then use the multiplication into addition rule on all of it. And you follow that route, and that'll lead you back up to there too. Let's practice going the other way. Sometimes going the other way is helpful. So let's go the other way. Reassemble many logs into one log. To do this, for you to be able to do this, the following must be true. All bases must match. And all coefficients, the numbers in front, must be 1. And then once you put them together, you should simplify inside if you can. So let's look at some examples. Example 1. We're going to have log base 4 of x minus log base 4 of y plus log base 4 of z. You can do them one at a time if you'd like. Subtraction turned into division on the inside. And then addition on the outside turned into multiplication on the inside. X over y times z, I can put the z on top. Let's look at some more. You guys give these a try. We're going to start off with 4 log base b of r minus 5 log base b of t. Okay. Hopefully you paused and you've worked on this. We need the coefficients to be a 1, which means I need to move all the coefficients inside as exponents. And now subtraction turns into division. Another example for you. We've got 1/3 log base b of x plus 2/3 log base b of y minus log base b of xy. Try working that one out. It's allergy season. I don't have COVID-19. Been staying home, staying healthy. Instacart, haven't even had to go outside to get groceries. Okay, hopefully you paused and worked on it. The first thing we're going to do is we're going to move those numbers outside up as exponents. And now we can put them together. And I'm doing these in steps. If you can do multiple steps at once, please do so. Now I've got them all as one big log, but it's not simplified. I have x's and y's on top. So one handy way of doing this is rewrite everything on bottom as a negative exponent. And when we have, remember the property, x to the m times x to the n equals x to the m plus n, we can apply that here. Log base b, we have x to the 1/3 plus -1, y to the 2/3 plus -1. So we have log base b of x to the -2/3, y to the -1/3. And if we want to write it without negative exponents, we can move it to the denominator. Log base b of 1 over x to the 2/3, y to the 1/3. And if you wanted to, you can write that in radical form. So there are several ways of writing things. That's the ideas behind 4.3. We're going to do 4.4 now as well. 4.4 only adds one more rule, but it requires you to actually start working with the calculator sum. So we're going to discuss calculator usage. Now, everyone's calculator differs. And if you get stuck, don't know how to use your calculator, maybe you can send me a picture of it, and then we can Zoom together and I can explain how to use it. But 4.4 is on basic calculator skills. and the change of base formula. It also has a couple word problems in this section, and we'll discuss what they're done and how you do them. So let's start off with some notation. If you see log x and there's no base, what this means is this is log base 10. So no base implies base 10. Why? Most people have 10 digits on their hands and their feet, and it's just the way we've done our number system. Our entire number system is based on powers of 10. At least modern times. Babylonians and different systems used different. They had base 30, base 60, some crazy bases. And if you see this notation, ln, I'm going to write ln like that because my l's look like 1. ln of x means log base e of x. ln stands for natural log because e shows up in nature. So much. So ln of x, also ln of x like that. It's all the same. So let's look at, we're doing some stuff with logs, these things, then we'll shift to doing their calculator versions. So what does log of 10,000 equal? Well, this is log base 10, and I can rewrite 10,000 as 10 to the 4th power. The 4 can come out, and log base b of b is 1. So log of 10,000 is 4. If you see ln of e, this is log base e of e. Same base as the argument equals 1. That's important. You should memorize this. ln of e equals 1. It's worth memorizing. Okay, so let's look at playing with the calculator some. So let's look at my calculator. And I'll try to show you where it shows up. I have a log key right there and an ln function there. Notice above them, I don't know if you can see it. See if I can tilt it right. Above the log, I have 10 to the x, and above ln, I have e to the x. So my calculator has buttons log, and above it says 10 to the x, and I have ln, and above it, it says e to the x. The reason why is they are inverses. And so the computer or the calculator keeps them close. If your calculator is like mine, Let's just take a look at a number. Let's look at log of 341. This means log base 10 of 341. For me, I have to type in, I'll hit the log key, and then I'll push in 3, 4, 1, and equal sign. Log 341 equals 2.53, maybe to 3 decimal places. It's approximately that. Some calculators make you type in the number first and then hit log. So I'll spell that out. This is easier to show in class, but this is the best I can do. Some calculators require 341, then log. Right now, you should try this on your calculator. Find out how your calculator works. I'm showing you what the answer is. If you can reproduce this answer, you're good. Your task right now, pause the video. Get this same answer on your calculator. Remember, you can YouTube just about anything. Using log on, my brand is Casio. I could type that in. There's got to be a video, at least one, showing me how to do it on a calculator. If you don't know how to do it, use the internet. Don't just play helpless. You're not helpless. I get a lot of students that play helpless, like they can't figure it out. In class, that's one thing. You just want to walk up and you're like, I don't know how to do it right now. I don't want to interrupt class by watching YouTube in class. That's one thing. Right now, we got to work from home, so we got to be smart. Look this stuff up, okay? If you still can't figure it out, ask me and I will show you how to use your calculator. I won't have a calculator with me that I can show you, but if you send me a picture, I can describe the steps of doing it, okay? Also try this one. Log of 0.06894. Let's see what I get on mine. Log of 0.06894 is approximately negative 1.16. Let's go 4 decimal places. Okay. Natural log works the same way. I'm going to use the natural log key instead of ln. There we go. ln of 341 5.832. And try doing ln of that last one. Negative 2 point, I can't read it very well with this angle, 6745. If you can get those 4 values on your calculator, you know how to use your calculator, okay? Let's take a look at the change of base formula. So change of base formula. Suppose I have log base 2 of 5. That's not in my calculator. There is no log base 2 in my calculator. If you've got a super nifty calculator where you can type in different bases, I've never seen one, but I bet nowadays they have them. I bet they do. Then you don't need to do this change of base formula. But you should know how to do it because it's just as quick, and I think it's easier to learn than learning how to use a complex function on your calculator. The change of base formula says I can rewrite this as any base I want if I do it as division. I'm going to treat it, I'll take the argument on the inside, I'll put it on the top, and I'll take the old base and I'll put it on the bottom. So that went there, and that goes there. Any base I want. So I could do b equals 10, and this works in the calculator just fine. Or I could do b equals e, and I could have ln of 5 over ln of 2. Let's compute both of these. Log base 5 divided by log base 2. See it in there? Log base 5 divided by log base 2 is approximately 2.322. It doesn't matter which base I turn it into. I can do this with the natural log key. Natural log of 5 divided by natural log of 2. Oops. And I still get 2.32. So that's how the change of base formula works. It makes it so we can take something that's in a complicated thing where it's not easy to figure out the number, turn it into bases that calculators can work with easy, and then calculate what we need. Why don't you guys try log base 3 of 7? So we can rewrite this as log base b of 7 over log base b of 3. Doesn't matter which base system you work with. I did ln of 7 divided by ln of 3. I get approximately 1.771. Okay. So let's look at some examples they use in this section. They're going to ask you problems on that involve pH system from chemistry. So applications. One is physics, one is chemistry. Chemistry one. The pH of something is defined as the natural log of H3O plus, where H3O plus is the hydronium ion concentration in moles per liter. pH measures acidity or alkalinity. Or acid/base. just so you know, pure water, nothing in it, has a pH of 7. And it's not, that's completely neutral. Not acidic, not alkaline. pHs greater than 7.0 are considered alkaline or a base. And if the pH scale is below 7.0, it's considered acidic or an acid. And we commonly round them to the nearest 10. So a couple examples of using this. Find the pH of a solution with an H3O concentration of 6.8 times 10 to the negative 8 moles per liter. So we use the formula we just had. pH is the negative log of the concentration. So I'm going to do 6.8 times 10 raised to the negative 8. And what that does is it moves the decimal left 7 times or 8 times, but it's so many in the calculator it doesn't show it. And then I'm going to say log of my answer. So in my calculator, this gave me negative 7.16749. And the two negatives cancel and I get 7.16 is 7.2. So it's slightly alkaline. And another example we can do. Find the pH, or find the concentration of H3O plus given pH equals 4.3. So this tells me the pH is 4.3, and that equals negative log. I'm going to type in or put in X rather than, this is X. So if I multiply both sides by a negative number, I get log X equals negative 4.3. And this is base 10. So I can rewrite this as X equals 10 to the negative 4.3. And just throw that in a calculator. 10, the caret sign right here, this symbol right here, usually means exponent. In fact, MATLAB, if you push that, type that in your keyboard, it'll move it to the exponent thing. I'm using parentheses because I want to make sure it doesn't screw up. And I get x equals 5.0119 times 10 to the negative fifth. And we'll make that 5.0. We'll round to 5.0. Another application of this is measuring the loudness of sound. So that's your chemistry examples. So in physics, our physics example, measuring the loudness of sound. You may have heard of this. It's called the decibel level. And it goes by dB. And the way they do it is they assign the threshold level or faintest sound you can hear. They call that I with the subscript O. I is for intensity. So IO is the lowest intensity we can hear. And the way the decibel system works, D equals 10 log of the intensity of our sound over the base intensity, the lowest intensity. So I is the current sound level. So they'll give you something like this. Find the decibel level I think they're just using D as the decibel level here. Find the decibel level of a sound with an intensity of 10 million times the faintest sound you can hear. So it's 10 million times louder than the faintest sound. I don't know if that's loud or not. Well, let's figure out what it is. D equals 10 times log of 10 million IO over IO, which is 10 log 10,000 or 10 million and that's 10 times log, this is base 10 of 10 to the 7th. And we can bring the 7 out front. Log base 10 of 10 is 1. 10 times 7 is 70. It's 70 decibels. I don't know if that's loud. Let's look it up. How loud is 70 decibels? Conversational speech is about 60 to 70 decibels. A whisper is around 20 decibels. Interesting. So not really loud, normal conversation scale. They've also got another one in there. I think there's one problem with it. It's measuring the age of rocks. So this is geology. Using, they're called atomic clocks. And what it does is it measures the amounts of argon 40 and potassium 40. In a rock. Now, argon goes by A. Potassium is K. And they give the formula time equals 1.26 times 10 to the 9th times the natural log of 1 plus 8.33 times A over K. So that's inside the natural log. I'm going to make that a bracket. All over the natural log of 2. And A and K are the number of atoms of argon and potassium. And they might go like, how old is a rock? Where A over K equals 0.325. I got rotated there. Just plug it in. T equals 1.26 times 10 to the 9th. And T is in years, mind you. And then we have the natural log of 1 plus 8.33 times 0.325 all over natural log of 2. So I'm going to just do this real slow. I'm going to say, what is 1 plus 8.33 times 0.325? That gives me what's inside here. I'll say I'm going to take the natural log of that and get that. Now I'm going to divide it by the natural log of 2 because it's on bottom. And I get that. So right now I'm at 1.26 times 10 to the 9th times 1.890349407. And if I multiply that in, oh gosh, that's old. 2,381,840 years. There's some, oh hell no, that's another comma. 2,381,840 253. 2 billion years. Good God, that's an old rock. Right? So they'll give you problems like this. This is 4.4. I will point out most of 4.4 is calculator work and change of base. These are very important. Skills. However, there's a lot of word problems in there. I think there's, oh, what was there? 33 problems and like 8 of them are word problems. I am going to make 4.4 extra credit. You should do at least the calculator problems and the change of base problems. Okay? You should. I'm going to test you on them. I'll tell you that right now. You will be tested on them. So go from there. That's motivating you to get some extra credit work in. That will cover 4.3 and 4.4. 4.5 is on solving equations that have logarithms and exponentials in them. We'll take a look at that. And 4.6 is on applications with logarithms and exponentials. Peace.